Hello, in this section we're going to be doing the first of 3 videos on the horizontal and the vertical movement of air and the Coriolis effect. So let's get into it. We're going to describe the vertical movement of air first and convection. Convection can go up into the atmosphere and it can sink down out of the atmosphere. Wind is the horizontal movement of air only. Right? In talking about convection, let's look at the sinking moving of air first. That sinking atmospheric air up high, as in the purple column there, produces surface high pressure when it sinks. There are 2 ways to sink that air from the atmosphere. The first way is what you see there in those columns. The first way is to add air into that low pressure area. You just add air molecules. The second way is to cool the air in that atmosphere at that elevation, and that's more likely. But either way, either one of those 2 ways, that increases the density of that purple parcel, and the gravity pulls down on that additional mass. And as you get near the surface, the parcel weighs down on the area at the surface or underneath. That develops your surface high pressure. A mnemonic for this is sinking sky, surface high, often dry. Now, the often dry part, where does that come into it? The often dry part of it is a physical manifestation of what's happening as this parcel sinks out of the atmosphere and toward the surface. As this parcel sinks, it moves into an area of the atmosphere that has more pressure. That pressure is pushing on that parcel. In doing so, it gives the molecules that are inside that parcel less space to bounce around in. And with less space to bounce around in, those parcels will hit that wall harder and bounce around harder. They'll have more energy. With more energy comes more heat. With more heat comes more temperature. This is known as compressional warming. And that compressional warming in turn dries out the moisture in the parcel. And in fact, the parcel now has a higher temperature and a higher saturation vapor pressure as well. So it is going to have less saturated air inside the parcel. So remember the memory cue. Sinking sky, surface high, often dry. Now you may say to yourself, this is fine for subtropical highs. They're warm from the very start. But what about these Arctic highs? Especially the Arctic highs we see on the map here. There's one up in North Dakota, and that's the one we're going to talk about there. Because where is the warming for the one in North Dakota? It doesn't seem like it would be very warm to me. But in these cases, remember, we're talking about sinking from high up in the atmosphere. There's a long way to go down. That warming happens in the middle of the atmosphere, in the lower atmosphere. It may not get to the surface. And all of that weight that's pushing on the surface acts to keep the surface air mass right in place. So it's very hard to move because it has a lot of weight above it. The surface air mass might keep its own temperature characteristics. Let's look into this a little bit more. When this sinking atmospheric parcel drops and warms, it may stop sinking and produce an inversion. After all, it's still buoyant, falling into colder air. It's not going to fall farther into colder air. It's going to remain buoyant. So it can remain buoyant and stop sinking and produce an inversion. And we know an inversion produces a very stable atmosphere that is stagnant. That's why when you have surface air underneath it that is dry, it will remain dry because the sinking sky makes the surface high that is often dry. And it's got dry air above it because that dry air evaporated off with the compressional warming. Hope that helps you out a bit. Let me talk a little bit more and show you two soundings that will help you out. On the right there is a sounding from the Arctic high that correlates with the date that you see in the map above. And look at that, you see two inversions low down in that atmosphere, like a double inversion, a very, very stable atmosphere that is going to keep the continental polar air that came down out of the Arctic right in place over North Dakota. Look at all the clear skies right around there. Sinking sky, surface high, often dry. Now, you may say, well, look, there are two other highs on that map, and you're not talking about those. And those highs are along the eastern seaboard. And guess what? There's rain all around those highs. But these highs are actually acting as blocking highs. Look at Pennsylvania. Look at New England. They are clear. Those highs are containing that very powerful warm front that is down along the Gulf Coast. So while you see rain in those East Coast high areas, you don't see the severe thunderstorms. You don't see the heavy rain and flash flooding that is associated with the warm front that is south of that. Now, correspondingly, you can look at rising atmospheric air. Different story. Rising atmospheric air and that vertical convection to go up produces surface low pressure. And that's a little bit easier to understand because you know from the pink column over there that hot surface air rises and expands, and as it gets higher up in the atmosphere, it starts to cool and condense. You know that. It produces tropical surface lows. It produces hurricanes. Here's your memory cue. Rising slow, surface low, clouds to blow. Why did I put in rising slow? Because that air and that convection current will move slowly. Gravity will be pulling that air back down again. So you will have a buoyant force that is tempered in its speed by gravity. Rising slow, surface low, clouds to blow. And you may understand this really well for subtropical lows that produce hurricanes. But what about Colorado lows? Look at what is highlighted on the map there. A Colorado low just on April 18th. And certainly that's not hot rising air. What's going on there? Actually, the southern side of that low does get warm during the day. And that daytime warming on that southern side and the moist air in the very cold atmosphere results in infrared emissions, especially overnight, and latent heat of condensation and convective lift. So there is a low there, and there is rising air there that is warmer than the atmosphere. Think of it in terms of this memory cue. Rising slow, surface low, clouds to blow. That's happening here as well. To go into horizontal wind, the force is much more powerful. It's a pressure gradient force. It pushes the surface highs toward the surface lows. And in fact, you see this with the pressure gradients from Hurricane Sandy. Especially when there's no friction out over the ocean, you can see where those pressure gradients are tight. Those are some of the strongest winds that you see on the map. Where those pressure gradients are over land, where there is more friction, and where they are broader, you see that the winds are really quite a bit lighter. So we just reviewed convective up and down vertical movements of air, which tend to be slower but very important. And we reviewed horizontal and pressure gradient forces, which are also very important and much faster. We need both to circulate the air in our atmosphere, and we'll go on to the next video for that.